Okay. Well, good morning, everyone, for this special scheduled seminar. Today, Maggie Bruckner, my graduate student, will be presenting the results of her master's research. The title of her talk is Indirect Validation of Ozone Mapping Profiler Suite, OMPS-Limbs Profiling Retrievals. And the motivation for this study is Maggie's plans to begin assimilating the OMPS data within our global chemical data assimilation system. And so this is the first part of that process, which is evaluating the fidelity of the measurement. Maggie got her degree in environmental science with a minor in chemistry at the University of Portland, where she did some work doing measuring atmospheric stability with both drones and tetherson systems. And since she's been at UW, she has been doing a lot of work developing tools for analysis of both model data, satellite data, and airborne data, and sharing those tools with groups that I work with, including the Lake Michigan Air Directors Consortium and also the Maryland Department for Environment. So again, today Maggie's going to be talking about her MS work, and I will let Maggie proceed.
All right, thank you, Brad. So let me start sharing my screen here. Wrong button. All right. So as Brad stated, my title of my talk is an indirect validation of the OMPS-Limb retrievals, where we're using a multitude of tools. Ozone is formed in the stratosphere primarily through the Chapman mechanism, where UV radiation separates ozone molecules, and then we have a combination to form, and then is destroyed again through UV radiation. But this mechanism isn't sufficient to completely explain the concentration that's seen, and an additional loss mechanism for ozone in the stratosphere is through catalytic cycles. The chlorine cycle, which is shown, or which I've shown here. So satellite observations of ozones have been made fairly continuously since the 70s. The current, or the latest generation in this is the Ozone Mapping Profiler Suite, which has a limb module and a nadir module. Nadir observations will give you a total column measurement, which have been done historically with the TOMS, GOM, SkyMackey, and OMI instruments, but we can also obtain a profile measurement using limb sounders or through solar occultation. And the main instruments that have done limb sounding are the MLS and the solar backscatter ultraviolet instrument. So one way that we can use these measurements is in chemical reanalyses, or is to set up some of these meteorological reanalyses are MERA-2, which only does ozone and aerosol, the Japanese reanalysis for aerosol, and the Copernicus atmospheric monitoring service under the guise of ECMWF has done a full chemical reanalysis. Ours is the real-time air quality monitoring system, Aura Reanalysis, and the value of these reanalyses is that our forecasts can be better constrained through the use of satellite observations or other measurements. And our validation here of the UMPS measurement for ozone is designed to obtain a better estimate of our observation error. So what we're doing is obtaining a bias estimate for the UMPS UV and visible retrievals through an indirect validation. This is different from the more traditional validation scheme where you need two observations that are occurring within a set time and distance from each other. Here we are taking observations from the ACE-FTS solar occultation instrument, finding coincidences within our RAQMS Aura model, and developing a bias correction that is the median difference. We then validate this correction using ozonesondes, where we find coincidences between the ozonesondes and our model. And then we take the model and that we have now validated a correction to and find coincidences with our new satellite observation and calculate biases. And so a little bit better overview of our method is that we sample the RAQMS Aura within a degree and 3 hours of the ACE retrievals, which is based on our on RAQMS. And then we remove our physically unrealistic outliers from ACE-FTS using a procedure that is outlined by a 2015 paper where a multiple Gaussian is used to define points that are far away from what's expected. And then we use the medians to develop a correction factor that is a combined median difference for a sunrise and sunset retrieval. We then look at validate this correction with our ozonesondes that will be discussed a little bit later, and then look at the comparison between our OMPS-Limb and our corrected RAQMS Aura. So the real-time air quality modeling system is Aura Reanalysis is a reanalysis of the RAQMS Aura global scale full stratospheric and tropospheric chemistry system between 2006 and 2016. Observations of ozone, aerosol, NO2, and CO are input using the operational grid point statistical interpolation 3D VAR system. The RAQMS Aura reanalysis is a 1x1 degree horizontal resolution with 35 isentropic levels from the surface to about 60 kilometers. And we save the full chemistry fields in 3-hour analysis increments. The OMPS-Limb profiler was launched in 2012 and is still currently running. And this was launched on the SUMI NPP satellite. We are using the retrieval version, NASA's 2.5, and the spectral range of the instrument is 290 to 1,000 nanometers, and it's a polar orbiter with a visible retrieval that goes from about 10 to 35 kilometers and a UV retrieval that goes from 30 kilometers to 55 kilometers in the atmosphere. The first part of our validation is retrievals from the Atmospheric Chemistry Experiment Fourier transform spectrometer, which is a solar occultator that was launched in 2003. We are using the version 3.6 retrieval. It's a high accuracy measurement, but somewhat infrequent because it, as a solar occultator, it requires the measurement to be looking directly through the atmosphere at the sun. So there's about 30 profiles a day with measurements made at sunrise and sunset locally. The annual sampling locations can be seen in the bottom figure. And so you should note that sunrise and sunset measurements make measurements of the poles at different times of year, which will influence these statistics as those are where you expect to see the largest variation throughout the year in ozone. And the ozone retrieval, or their ozone retrieval, is from 10 kilometers to 95 kilometers in the atmosphere. And the bias estimate of the measurement is plus 2% below 45 kilometers and from anywhere between 0 and 19% above 46 kilometers. To validate our ozone correction, we use ozonesondes from the ESRL and SHADOWS networks. The SHADOWS sondes, we've selected 3 that are in the tropics, approximately evenly spaced across the globe, and then the listed ESRL sondes, which are primarily in North America. So moving on to looking at our zonal median profile between 2006 and 2016. First here is the SR medians and then the SS. And some important parts of this to note are that in our tropical troposphere, RAQMS Aura is underestimating the maximum concentration of ozone, and then between the SR and SS measurements, our largest areas of disagreement in the median profile is at the poles, which is likely due to our variation in sampling pattern. And then as part of building our median correction, our correction factor, we decided to look at the variation as the median absolute deviation for, again, SR and SS retrievals. The variability, or the difference in variability between the ACE observations and the RAQMS Aura concentrations is fairly similar in both cases, with some very small differences in ppmv up high and a little bit kind of in the polar regions, but again, very, very small differences. And then our bias correction, since our variability is similar between the measurement and our simulation, we looked at our median difference between the retrieval and the model. And then, since they're fairly similar with again, a little bit of polar difference, which is expected based on the sampling pattern. We then combined the difference to create our bias correction that we will apply above the tropopause. And the difference in our RAQMS is primarily biased low compared to our ACE-FTS measurement. So now that we've got our bias correction, we are validating it by comparing to our coincident ozone sondes. So here I'm showing several scatter plots that on the left-hand side show our average or our relationship between our RAQMS ozone and our measurements for both the azurosondes and the SHADOSondes. It's fairly the two are fairly in mean agreement. And then on the left, I'm showing our impact of the correction compared to the ozone sonde measurements. You can see that the largest impact that the correction has is for our when the ozone sonde concentration is below 100 parts per billion by volume. But for the majority of observations, the correction is about 25% of the actual, or less than 25% of the actual measurement. Now looking at these in more of a profile format, we're looking at the mean percent bias before the correction and following that correction. In the azurosondes, we have primarily a lessening of the bias, whereas it's a little more variant for the tropical sondes. And then we also look at this relative to the tropopause for the SHADOSondes, where it can again be seen that there's a little bit of an increase in the bias following the correction. This is so the important thing to note here is that our bias in our model is high in the below 30 kilometers. So now that we've got our bias correction created from median ozone the median concentration relative to ACE and have kind of benchmarked it relative to the ozone sondes, we then look at coincidences between our model concentration and the OMPS-Limb observations between 2012 and 2016. And there is a coincident validation that has been done, and so we compare our results found through indirect validation to that. So here we are looking at the mean bias in the OMPS-Limb UV retrieval, which is above 30 kilometers to about 55 kilometers. The difference between the observation and the model is within plus or minus 10%, with some high bias in the lower portion of the retrieval, and above 45 kilometers and below 50 kilometers were slightly, the retrieval is slightly lower than the model, or than the corrected model. This agrees fairly well with the coincident validation. And then moving on to the bias in the visible retrieval compared to our coincident corrected model, excluding some variation in the tropical troposphere. We're primarily biased, the retrieval is primarily biased low, but is still within about plus or minus 10%. The difference that we're seeing in the tropical troposphere is different than that seen in the direct validation study, where they're using the Aura MLS, which we assimilate in the model. And because our ozonesondes indicate that the model value for ozone is high in the troposphere, we believe that this difference is likely larger than we've calculated here. But because we're using more observations than, or more points of comparison in an indirect validation than a direct, this indicates the value of our study. So then we look at the mean annual cycle, comparing between the OMPS-Limb and the corrected RAQMS Aura. We've done this at across the entire globe, but are looking primarily at the listed 3 regions. And we calculate this as the variation in percentage from the mean concentration. And the difference seen given in the third plot is RAQMS removed, or the RAQMS cycle removed from the UMPS. And so a positive value indicates that the cycle, or that the deviation from the average concentration is larger for UMPS than for RAQMS. And this difference is about on par with what we're seeing for the mean difference, with about within plus or minus 10. But there does appear to be some seasonal variability to the magnitude of this difference. So some of our conclusions are that the RAQMS Aura ozone mixing ratios are generally biased low relative to the ACE ozone retrievals, and high relative to the ozonesondes. This bias can be reduced, and the bias is able to be reduced through our correction. The OMPS-Limb, UV, and visible ozone retrievals outside the tropical troposphere are biased low by less than 10%, which is consistent with the previous direct validation. The high bias in the tropical upper troposphere is a little bit different than the previous results, and is still likely underestimated based on the tropical sonde comparison. The average seasonal cycle is fairly similar between OMPS-Limb and our model. We have now found calculated observation error statistics for the OMPS-Limb, UV, and visible ozone retrievals, and they indicate that assimilating the OMPS-Limb retrievals would have a positive impact on our model analysis. And so we are now looking into moving forward on the assimilation of the OMPS-Limb ozone retrievals into the NOAA Unified Forecast System with RAQMS Chemistry. Where we're going with this is we've done a limited period with the new Unified Forecast System with RAQMS Chemistry, a new simulation that runs through from July to September 2019. That is a free-running simulation that was initialized with RAQMS forecasts, and we're focusing on this period because it the FireX AQ field campaign that looks at that's looking at ozone or at chemistry of forest fire emissions, and the I've shown a comparison of, for the UV and visible retrievals with our new forecast, and the differences are fairly similar to what we saw with our longer period. And so hopefully we'll see a positive impact on the model. Thank you.
Well, thank you, Maggie. So we have time for questions. You can unmute if you have questions.
Yes,
Jack?
Yep. Yeah, good presentation. I'm wondering what the reason is that you're using the ACE-FTS instead of SAGE for validation. Back in the old days, everything was, SAGE was looked at as sort of like the gold standard.
Yeah, I believe that, so I'm familiar with a little bit on the SAGE. I don't quite know the time period on that one. The ACE retrieval is fairly high accuracy, and we get a the version of the retrieval that we're using has measurements at every, I believe it's every kilometer between 10 and 95 kilometers. And we get global coverage, whereas I believe that the current one that you mentioned is just on the, SAGE 3 is just on the ISS, correct?
I believe that's correct, that's the only SAGE operating, so. But,
yeah, so we thought that we were getting a good measurement at a bunch of locations across the globe.
that's a good answer.
So for those of you that don't know Jack Fishman, Jack is was a NASA scientist at NASA Langley for a long time and is one of my mentors. He's now at St. Louis as a faculty member, and he's on Maggie's committee. So welcome, Jack. Any other questions? If not, I have a question. So you did both the UV comparisons with UV UMPS and the visible UMPS retrieval. How in the region where they overlap, how consistent are they? And I'm wondering if you're anticipating any issues with assimilating both of those in that overlap region.
So I probably should have thrown in my figure for, I have calculated and shown some of the differences between the two.
That's okay, you don't need to.
Okay, yeah. There are expected, so within kind of the 62, or between about 40 north and 40 south, they're fairly similar, or the two are fairly similar within the overlap area that's between about 30 and 35 kilometers. But then kind of outside in more the polar areas, there is a larger difference between the two retrievals, which I expect that we can't just create a combined retrieval to look at or to include in the model, and we need to at more and kind of keep them separate,
Okay.
which introduces some complexity to the assimilation process.
Thanks. Okay, do we have any other questions? Aditya, did you have a question?
No.
I do see a lot of comments. Oh, those are all claps. Good.
You're just
Okay.
clapping.
Okay. If there's no more questions, we'll close this. I would like to have Matt Hitchman and Jack Fishman and Maggie stay on just for a little while so that we can deal with some of the formalities of the MS warrant page. And otherwise, thank you very much for joining us for this special seminar by Maggie.
Thanks, Maggie.
So Pete, if we can stay on just for a little bit longer.
Yeah, that should be no problem at all. It should stay open even after I leave. So you guys should be. I should
Okay.
stop recording though.